better add up to be, right? It better add up to be 100%. Because once you know each of the elements in terms of their individual percentages, they represent the only components of the chemical compound. So I want to know what's the empirical formula for this compound. Okay, now let's think about this. We need to find the subscripts for a chemical compound, right? The subscripts are based on mole ratios, right? We're given percentages, and percentages aren't moles, are they? Okay, percents aren't moles. Okay, to get those mole ratios, all right, let's remember that they have to add up to 100%, right? So if I take 64.82, 13.59, and 21.59%, that adds up to 100. Right? Now, let's say I equate those percentages to grams. If I equate those percentages to grams, then those percentages as grams must add up to 100 grams, right? In other words, I'd have 100 grams of the compound, which would yield 64.82% carbon, or grams of carbon. It would yield 13.59 grams of hydrogen, and then 21.59 grams of oxygen. Now be careful. When we're talking about elements in a compound, especially elements like hydrogen and oxygen, they are monatomic, right? So it's H and O. When I talk about hydrogen by itself and oxygen by itself, I'm talking about H2 and O2. So in a compound, chemical elements are monatomic on their own. On their own, in the atmosphere and around, they are diatomics, right? So if I say hydrogen, I mean H2. If I say hydrogen in a compound, I mean H. If I say oxygen by itself, I mean O2. If I say oxygen in a compound, that's O. Okay. So if I have grams, I can convert to moles, can I? Sure. Yeah. One of the yells in Chem 1A is, when in doubt, convert to moles. So if you're given grams, you can convert to moles. And how do we convert grams into moles? You use molar mass, exactly, right? So I take the grams of each and convert them into moles using molar mass. Remember, we've been doing this before. If you've kind of following what's been happening since the beginning, we're building upon every little thing we learn. That's one of the things about chemistry that prevent you from getting behind. If you skip a step, right? If you miss out on something and you get behind, you're going to lose out on moving forward, because everything we do builds upon itself. All right. We may take a couple of left-hand and right-hand turns away from certain stuff, but right now everything is building upon itself. So if you're weak with something and your foundation's not there, you could have problems moving forward in the class. So I got 64.82 grams of carbon. Remember, the percents equal the grams. I know that carbon has a molar mass of 12.011 grams per mole. So I take those grams and I convert them into moles. So that means I end up with 53.97 moles of carbon, right? So that's how many moles of carbon correspond to 64.82 grams of carbon. I got 13.59 grams of hydrogen. Okay, that's the hydrogen that was in the sample. Okay, remember, hydrogen in a compound is always monatomic. So I use the molar mass for hydrogen, not H2, hydrogen. So that's 1.0079 grams for every 1 mole. So now I've got 13.48 moles of hydrogen in 100 grams of my sample. Then I've got 21.59 grams of oxygen, and I'm going to use the mole, back over here again. Same applies to oxygen as did with hydrogen, all right? There's 15.994 or 16.00 grams of oxygen for every 1 mole of oxygen, which gives me 1.349 moles of oxygen in the 100 grams of sample. Now, I can't use these numbers as the subscripts because notice they are not whole numbers, right? If I were to write, the compound is C 5.397, H 13.48, and then O 1.349, that's not correct because chemical compounds are made up of elements in whole number ratios, right? So what I got to fix this problem is go through and simplify by dividing by the smallest numbers of moles, all right? So we'll take each of the individual moles and divide it by the smallest number of moles to gain a whole number ratio for each element in the compound. So the 100 grams gives us total moles in 100 grams. the division by the smallest gives us the simplest whole ratio of moles in the compound. So I had 5.397 moles of carbon, 13.48 moles of hydrogen, 1.349 moles of oxygen. Right? Those are the numbers we calculated based on 100% and 100 grams. These will now yield the subscripts X, Y, and Z in the compound. So to figure out the subscript for my carbon, I would take the moles of carbon, which is 5.397, divided by the smallest moles, which was 1.349 for the oxygen. So that's my subscript for the carbon. Find subscript for my hydrogen. Okay, I would take the 13.48 moles of hydrogen divided by the smallest moles, which was 1.349 moles of oxygen. That's my subscript for the hydrogen. And then I would take the moles of oxygen and divide it by itself just to make sure my calculator's working. You never know when that thing's going to go haywire, right? Just make sure it gives me a 1. And so that's the subscript for my oxygen. And we see we get pretty good whole numbers, don't we? Right? 4.001 is pretty close to what? Yeah, 4, right? Okay. If I've got 9.992, that's pretty close to what? That's right, 10. Good. And then 1 is 1, right? So that means our empirical formula is going to be C4H10O, and I cannot simplify that further. Now, if it was the case that I could, well, then I would just do so, right? If I ended up for somehow doubling everything up and I got C8H20O2, I would say, well, that's not the empirical formula. It's got to be simplified. So that's C4H10O. See how this works? Again, classic problem, Chem 1A. Take your percentages, assume grams, convert the grams into moles, divide by the smallest moles. Boom, there it is, okay? Now, to do that, you have to understand a lot, right? You have to understand about mole conversion from grams using molar mass. You have to understand the nature of a chemical compound and what those superscripts or the subscripts mean. So, as I've been saying all along today, the little bitty parts that we're working on, right? These are things that add up to the longer and more complicated problems. And if you have any missing components, then the solution becomes difficult or not impossible. Okay, now what happens if you get a ratio that comes out to be a fraction? Well, if you do, it'll generally come out to be something that's quite obvious, right? Something like 0.5, 1.5, 0.333, 667, so forth like that, okay? Let's say I came out and I did my numbers, and I got a number like this that came out C1.33H4O1. All righty. Well, I'll just round that carbon down to 1. No, that's a conspicuous number. Okay, that looks like something I could fix. In this particular case, I know if I multiply by 3, that would turn 1.33 into 4. Remember, if I have 1.33, that's actually 4/3. 4/3 times 3 equals 4, right? So I'm going to take that whole thing and then multiply it by 3. And when I do, I'd end up with the following empirical formula, right? C4H12O3, which at this point cannot be simplified, right? If I divide by 3, I would end up with a fraction again. So if you get a funny looking number, you will see a conspicuous fraction, something that you can fix, right? If I had 0.5, 0.15, those are conspicuous fractions. If you get a number that's weird, like 0.87 or 0.46 or something like that, you might want to check your calculation. Okay, you may have made an error somewhere. Go back and double check your work. So other examples are, let's say I had 0.5. Well, I'd multiply everything by 2 because that'll simplify 0.5 to 1. Okay, if I saw 0.25, I'd multiply everything by 4 because 0.25 times 4 equals 1. And last but not least, if I had 0.667, 2/3, I multiply by 3 to get 2. Okay, see how that works? Okay, so it seems like, wow, we're going real fast. And, Chem 4, we spent 6 weeks doing this. Yeah, we did. Remember, I'm going to teach Chem 4 in about a week and a half, maybe 2 weeks. And then we're going to go on and learn Chem 1A. So those of you that took Chem 4, this should be review. This should be stuff that you're very familiar with. You should have it all down. If you don't have it down, that's fine. You got time to get caught up by the end of this week, pretty much. All right? Because once we leave this week, we're going to move on. And it's hard to catch up after the second week. All right? All right, I got you a take-home practice 1. Okay, so we'll finish up on this one note. Okay, I want you to determine the empirical formula of a compound is as follows. 45.89% carbon. All right, so that's the amount of carbon.
And then?
There's 2.75% hydrogen.
And then?
There's 7.65% nitrogen.
And then?
There's 17.50% sulfur.
And then.
There's 26.20% oxygen.
And then.
No, and then.
Sure?
And then.
No, and then.
And then.
No, and then.
And then.
No, and then.
And then.
Okay, there's no more and then. All right, so you should get a compound that comes out C7H5NO3S. At this point, it doesn't matter which order you have the elements in. This is kind of just a convention that would be done. When you get to organic chemistry, you'll understand. So if you were to write those elements in different orders, that's okay. Don't worry about it. All right? It doesn't matter to me. But you should get C7H5NO3S, and that's the empirical formula. Would you see a problem like this on a quiz or an exam? Oh, hell no. No, I wouldn't do that to you, all right? That's too much time. But if you can do a problem like this and get it right, then you can do the simple ones. Part of the thing about learning chemistry is you want to work the hard problems so you can do the simple ones. Really, that's the case, all right? All righty. So where are we going to pick up? All right, so next time we're going to start in with what's known as the law of conservation of mass. This is going to get us into balancing chemical equations, which leads into chapter 4, stoichiometry and stuff like that, okay? So I am going